Well, welcome back to our class on system engineering. We're continuing to walk through our introduction and overview and of some of the basic knowledge of system engineering. And so these first three chapters gave a nice introduction to system engineering, model-based system engineering. And now when we get into chapter 4 and chapter 5, we're going to talk about some things that may seem a little bit abstract, but hopefully with what could be relatively short lectures, you'll get a perspective on how both discrete math and graph theory can be used in the system engineering process. So for this lecture, we're going to be talking about discrete mathematics, looking at sets, relationships, and functions. And the next chapter, we'll get into a different way of looking at that graphically. So here we're talking about discrete mathematics, and the purpose of discrete mathematics is to demonstrate the mathematical rigor for which system engineering must strive and to provide a language with which we can discuss key issues. Some of this is going to get a little bit advanced, and so we're not going to focus on that, but the area of requirements is an area where this is going to make a lot of sense. So examples of such important concepts are the distinction between a relationship and a function and why it is critical for engineering a system, a partition of the elements of a set that can be applied to many system engineering concepts, and partial ordering of functional execution. So functional layout, how you break things up into parts, how do we do our requirements and requirements verification. Those would be some things that we'll start to think about here. So the key concepts introduced here and used later in the text is, as for example, the requirements and requirement documents in chapter 6, we'll get a chance to see the relationship between discrete math and MAT. Many system level requirement documents are very large, which you could argue are larger than they need to be. And perhaps by using this kind of information, we could start to streamline that. So they can contain thousands and even tens of thousands of requirements. So the following are requirement examples that are part of the same set, but likely not acknowledged. And so keep in mind that these are all separate requirements scattered through the documents. And so attack from another computer system, buffer overflow attack, stack-based buffer flow attack from another computer, stack-based buffer overflow from an internal employee, buffer overflow attack against its operating system, against its applications program, attack originating in emails, and attack when connecting to websites or the internet. So we see this buffer flow overflow, the stack-based buffer overflow. And so a lot of these things are related. And is this really the best way to be capturing, say, this one functional area in the requirements? And perhaps with discrete math, we can start to come up with an alternative approach to flesh this out. So in chapter 6, we'll present an approach to writing such requirements and making the point that only one or a few of the above requirements should be the system level requirements document. SysML can also be helpful when we start to graphically think about how to be organizing things, and this will also get into the next chapter. We also use the concept of partition introduced and defined here in this chapter of our partition, which is based on set theory introduced in this chapter, ensures that the requirements are not overlapping and are complete. Satisfying the non-overlapping part will be relatively easy, but it's amazing how often it happens in practice. So, and then chapter 7, we'll discuss functions that systems perform and transforming their inputs into their outputs. When we have this discussion, we should remember the definition of mathematical function. What you may not have learned previously is the concept of a mathematical relationship, which is a weaker concept than that of a mathematical function. In order to perform a mathematical analysis of our system's functional architecture, we will need eventually be able to satisfy the mathematical definition of a function, not simply a relation, which is what we're talking about in this chapter. In chapter 7, functional architectures discussions talk about decomposing higher level functions into sets of lower level functions. And we can note that the word set is being used here again. The mathematical concept of composition is defined here in chapter 4 and discussed relative to hierarchical decomposition. Mathematical composition will be shown to be a very limited representation of the functional modeling described in chapter 7. So both power set and partial ordering are introduced. And these are advanced concepts, and so we won't get into them in detail. They have great usefulness in the theoretical development of the engineering of systems, which is also beyond what we're going to be talking about. But if you're interested, there are a couple references that Booty talks about. And an example here is it can provide a mathematical structure for performing early validation of requirements. And that is an important topic. And so you can see the context of why some of this may be a benefit, although it may get quickly beyond the sort of the survey perspective that we're trying to do in this system engineering course. Okay, so that's a little bit of a motivation. Now we'll have a handful of charts that get into some of the details of discrete mathematics. And so for sets, this talks about how to be writing set membership. And so X is an element of A, X is not an element in A. And so there's a couple of different ways that you could be writing that as we're showing here. For describing members of a set, A is in the set of elements X that satisfies a property P of X. So complete enumeration is the listing of all the members of a set. We can use the characteristic function of a set to help us to figure out what we're trying to accomplish here. And so here's an example. We can also think of using recursion in terms of a definition. Maybe some of you have had some programming experience and are familiar with recursion. If not, then maybe just take that in for something to be thinking about later. And we can use one or more set operators such as union, intersection, and complement to be helping us to describe sets. So here are a couple definitions and categories of special sets. First, we have U, which is the universal set of all possible members. We have the null set, which is a set with no elements. And whatever you want to be, phi has no elements, or not has no, null has null sets, where if we think of a null as a set, then there would be an element. You can maybe think of some sports stars are actually starting to have themselves having the number of 0 or 00, which in that case, it actually is defining a specific entity. A singleton set, this is a set when there's only one element. A finite set is where there's only a finite number of distinct elements. You can have an infinite set where you can have a series of some sort where it results in an infinite number of sets. You can have subsets or sets of inclusion, and then you can have equality of sets. And so those are some possibilities in terms of some special sets that we may bump into. Sometimes a picture is worth 1,000 words. And so here we can think of an inclusion. So A is included in B as we're thinking about this topology, the way it's listed. You can have an absolute complement. So if this is A, which is part of this universal set, then not A would be everything outside of A. And so we're showing that in a picture. You can have a relative complement, and so you can have B and A, and there's a little bit of an intersection. And so here we're showing B, not A, and so it's a B minus A, and so it's everything outside of where they have in common. And plus, finally, we have the intersection is where it's B and A, and so we have this area here between those two. So partitioning is an important concept. And so here in this picture, we have an example of a partition where we can partition because each is distinct and there's no overlap. But in this other example, B1 and B3, there is an overlap. And so therefore, this is going to make it a much difficult type way of having us to approach that. So partition on a set, A is a collection of P of disjoint subsets. And so this is why we're seeing here, if this is the totality of A, we have a lot of subsets. And so we can definitely put that together. So that's a concept that may end up being useful for us as we go forward from this class. Hopefully you'll find it useful. So we can have something called a power set. A power set is a set of all the sets that are a subset of A. So that's just another definition for us. In ordered pair, we XY, if X is an element of A and Y is an element of B, we can have a Cartesian product, which is A cross B is defined over two sets, A and B, such that A cross B has elements where A comma B, A is an element of capital A and B is a capital B is an element of capital B. That is a Cartesian product of the two sets, the set of all possible ordered pairs of those two sets. We can also have an ordered n tuplet. And so here we can have A1 cross A2 dot 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 all the way to AN cross AN. And so this is how that would be fleshed out and a little bit more complicated than just a simple Cartesian product. So we can also have a unary and binary relationships. A unary relationship of a set A relates elements of A to itself and a subset. We can have a binary relationship is a relationship of R that relates elements of A to elements of B and is a subset of A cross B. So just some more detailed types of definitions for us to sort of introduce the area of discrete mathematics. I won't go through this in detail, but there's a variety of way of proving implications or propositions. And so if you can come up with a discrete math equation, you can start to be figuring out some of these requirements problems or functional decomposition problems by proving it using a form of discrete math. And so that's the concept that I want to point out. And here are some various proving modalities that could be used. Here are a bunch of relationships in terms of discrete mathematic type of equations. You can have reflexive, irreflexive, symmetric, antisymmetric, asymmetric, transitive, and intransitive. So these are in the textbook. I'm not going to go through it in detail, but just trying to once again give some high-level introduction to some of the discrete math ideas. For relationships, you can have a couple possibilities. You can have partial ordering and you can have an equivalence relationship. A relationship R on A is a partial ordering if R is reflexive, antisymmetric, and transitive. And so in this last chart, we saw a little bit of information about defining those terms. A relationship R in a set A is an equivalent relationship if R is reflexive, symmetric, and transitive. An example of an equivalence relationship is equality. Okay, so we talked a little bit about sets. We talked about partitioning of sets. Now we get into this idea of a function. So from a discrete math sense, we can be thinking of a function. And so here is part of what that would actually mean is let A and B be two non-empty sets. We write a function as f, comma, as f colon A to B, and say that f maps every element of A, the domain, to one and only one element of B, the range. So you might be thinking of a function as a black box, and so there's an input and an output. And so with every input, there's a specific and unique output. And so that's what we're trying to describe here. And then we have some more specific thoughts on functions, as we can have a function that is called that has a one-to-one relationship. And so with every input, there's a unique output. So it could be titled a one-to-one or injective. We can have a function that is surjective or onto, and that is if and only if for f equals b, that is, f is defined for every b, which is an element of capital B. We can have a function that is both one-to-one and onto, or a term for that is bijective. Then the relationship, we have something that we're defining here as an inverse relationship. So A goes to B, and therefore B goes back to A. So there's a dual relationship between the input and the output. So we have a couple other types of perspectives here. First is composition. And so let R be a relationship from A to B, and S be a relationship from B to C. A comma C is an element of the composition of R and S, denoted R dot S or RS, if and only if there is an element of a B is an element of capital B, such that A R B and B S C. That is, that A and C must be linked together by B. A is a map to B and B is mapped to C. So we have two functions. So a block is tied to another block. And so there's something, an input to the first block comes out and then goes into the second block. And so there's a relationship. So we have a composition of two functions connected together. And this is starting to develop that concept in a discrete math point of view. So I know this may be a little bit abstract. Hopefully, when we start to be thinking about this in the actual physical modeling, it'll be a little bit clearer. But let's just give a summary over a couple of charts in words rather than talking about discrete math notation, or what this actually means. So the chapter gave an introduction to sets, the foundation of the branch of mathematics called discrete mathematics. A great deal of terminology is introduced. And so we just fairly quickly stepped through that, and I didn't want us to get lost in that and trying to think of more high level. And so by having this narrative summary, maybe it'll be more beneficial to help you see what we're talking about. So we defined a number of special sets, such as the universal and the null sets and operations on sets. During the discussion of sets, the concept of partition was defined. The partition is the most important mathematical concept introduced in this chapter for the application in this book. A partition is a subdivision of sets into subsets which contain no common members. And we talked about different types of requirements and how you're trying to make them so they're separate and distinct. And so if you can be thinking about how you've done a listing, a set of requirements, you may start to see how partitioning can be a useful thing. And there's going to be other modalities. The union of a subset contains every element of the original set. In future chapters, requirements will be partitioned, functional decompositions will be defined into partitions, and physical decompositions will be defined to be a partition. The power set of a set is a set of all subsets of that set. The notion of a power set is not exploited fully in this book, but it will become key to future developments and application of mathematics and the engineering of systems. That's what Booty contends and is continuing to do in his research. The chapter dealt with relationships, relations, and the key properties associated with the relationships. A relationship is a set of ordered pairs. The elements of the ordered pair comes from one set or two sets. If the function of the systems are not fully defined in terms of inputs, then these system functions and facts are mathematical relationships. And finally, just to finish up with this last comment for this chapter, functions are relationships that satisfy certain properties. A function maps every element of the domain of the function to some element of the range. So every input maps to an output, but it does not map any element of its domain to more than one element of the range. One-to-one and onto properties of the functions were also discussed. Finally, the composition of functions was defined. So that's it for this chapter, and thank you very much.